In this lesson, we're going to come up with an efficient way to prove that two triangles are similar to each other. Just like we had triangle congruence theorems, we had side, 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 side angle, side, etc., the 5 congruence theorems, there are a few triangle similarity theorems that we're going to learn. And we're going to start with the one that we're going to use the most. Given two triangles, we have triangle ABC and DEF. We have a couple angles that are congruent. The measure of angle A is congruent to D, and B is congruent to E. And these markings are just slightly different. They put a dot instead of the little, instead of the two lines that the two arcs that we usually use. But they still imply that they are congruent. We want to show that triangle ABC is similar to triangle DEF. Well, we're going to map one to the other, and we're going to map angle D over to angle A. So that's going to be a translation and then a rotation to line up the sides. And this is what we get. We have D and A at the same spot. So I do that again. Oh, that's a terrible arrow. But we translate D over to A and we rotate and we come up with this image right here. And now we also know, remember, that angle E, which is this guy, is now called B prime. They're also congruent. So I'm going to mark that off. And then take a look and see what you have. What happens here? What does this tell you? When these two are congruent, those are corresponding angles, and so we have two lines cut by a transversal such that corresponding angles are congruent. Well, that should tell you that these two lines are parallel. Okay? And that should also mean that these angles are congruent, which should make sense because if two angles in a triangle are congruent, the third one is also congruent. So what this shows is a dilation, actually, from point A of line B prime C prime to BC. And we've talked about lines that are dilated. When lines are dilated, they are in proportion, and the distances are also in proportion. So what we have here is this fact. Since we have all three pairs of corresponding sides with the same proportion, and we know that all three pairs of corresponding angles are equal, they have to be similar. So here's what we started with. We started with just two angles, and we've shown that the triangles are similar. This means we can use angle similarity to prove two triangles are similar. So all you need to show is that two pairs of corresponding angles, angles are congruent, and the triangles will be similar. So we actually have three criteria for proving similarity. We tend to use angle the most, but here they are. They're abbreviation, and then we can write up the segment or angle relationships. The first one is angle. And it says two triangles are similar if two angles of one triangle are congruent to two corresponding angles of the other triangle. So we could prove that. To prove that, all we would have to show is, for example, angle A is congruent to angle E, and angle C is congruent to angle G. That's sufficient to show that triangles are similar. But we could also do side angle side. Say we don't have information on two angles, we only have information on one angle. Well, two triangles are similar if two pairs of corresponding sides are in proportion and the angles between them are congruent. So again, the angle has to be between the two sides. So for example, with my images up here, if I have BC over FG, and that's equal to CA over GE, then the angles that you have to show would have to be angle C is congruent to angle G. It has to be the angle in between the corresponding sides. And then the last one, you don't have to use angles at all. If you could prove that all three pairs of corresponding sides are in proportion, then you can show that the triangles are similar. So that would look like this. BC over FG, CA over GE, BA over FE. If you could do this, then you can prove the triangles are similar. Now, again, the least amount of work is usually using AA, angle similarity, because it's pretty easy to get two pairs of angles congruent to show that they are similar. So here's a similarity proof for you. I'm given that AD and BC intersect at E, and AB is parallel to CD. So you really don't have any information about the sides. This does not say they bisect. That doesn't mean that E is a midpoint. All it says is that they are intersecting. So I want to prove the two triangles are similar. Well, we'll start with writing our given. And I shortened it just a little bit because I'm going to run out of space. But normally you would write the whole thing there. AB is parallel to CD, and it's marked that way. And that's our given. So we want to get two pairs of angles congruent. Well, if we start with parallel lines, we know that if parallel lines are cut by a transversal, then alternate interior angles are equal. So angle A is going to be congruent to angle D. So that's what we write. Angle A is congruent to angle D. And remember, our reason has to be the big long reason that we usually use for parallel lines. And here it is. If parallel lines are cut by a transversal, alternate interior angles are congruent. So we have one pair of angles. So there's one angle. Now we need the other pair. And we could have done the same thing. We could have written in one step, actually. We could have written that angle B and angle C are also congruent. But I'm going to put in the other reason just so you have it. Remember, this is the bow tie. So we also can have vertical angles are congruent. And that's what I'm going to write just so you have this extra reason here. So we have angle AEB is congruent to angle DEC. And my reason is going to be vertical angles are congruent. Well, we have two pairs of corresponding angles being congruent. That's enough to say that triangle ABE is similar, there's my symbol for similar, it's like the top of the congruent symbol, to triangle DCE. And that's by angle-angle similarity. Okay, and then finally, what similarity transformation maps one triangle to the other, the big one to the little one? Well, if you look, I'm going to shrink it down. And I think if you measure it, I forget what the exact ratio is. It looks like maybe a third. It could be that CE is a third the length of BE. So it's going to be a dilation. And the center of dilation is going to be at, we can dilate it around E. Well, I'm not really sure. So let's just say 1/3. And then we're also going to rotate 180. The order really doesn't matter here. Rotate 180. So we'll say we're going to dilate about E, and then rotate 180, also about point E. And that would map one to the other. In the last example, we have segment BS is perpendicular to TV, and angle 1 is congruent to angle V. So we already have one pair of congruent angles. And then here, if that's perpendicular, well, both sides are going to be congruent because they are right angles. So this is actually a very short proof. We want to prove that the two triangles are similar. So we write our given down. And in our given, we already have one pair of corresponding angles congruent. So now we just have to take care of the perpendicular lines. Well, we know perpendicular lines form right angles, and right angles are congruent. So here's our second step. We can write that BST is going to be congruent to BSV because perpendicular lines form right angles and right angles are congruent. So that's it. That's all we need. We have our two angles. So we have angle-angle similarity, and that's enough to say that triangle TSB is going to be similar to triangle BSV. And that's because of angle-angle similarity. So what looks like a complicated problem is actually pretty easy. Angle-angle similarity is probably one of the easiest proofs we can do because all you need is two pairs of congruent angles and you are done. The similarity transformation that maps one to the other, this time it looks like a reflection over SB and a dilation, probably about S, and it looks like if we were to map, does it say BSV onto TSB? So Looks like it's going to be a dilation about s by a factor of 2.